Okay, so the next speaker is Wenjie Fang, who's going to be speaking about bijections between planar maps and planar linear normal lambda terms with connectivity condition.
Thank you, Noam, for introducing the talk, and I'm very happy to come here today to talk to you about bijections, well, always bijections, between planar maps and some lambda terms with connectivity conditions as announced. Okay, this won't work. What? Yes. Ah. Okay, it's now good. So, I don't know a lot about lambda terms, I have to admit, because I do combinatorics. And so for me, lambda terms are simply some kind of unary binary trees. Well, the syntactic tree, what we call, and we also call it a skeleton of a lambda term, plus some identification of which variable, the variables are leaves, points to they come from which abstractions which are unary nodes in the unary binary trees. And of course, what remains are the binary nodes which are applications. Okay, and in this talk we are mostly interested, in linear lambda terms, which means that there is a bijection between one-to-one correspondence between variables, so leaves, and abstractions, so unary nodes. So this is an example of linear lambda term. And well, of a linear lambda term, and we see that when we do the variable abstraction map, we more or less we can represent it as a diagram in which each leaf is converted to a flash, well, to an arrow that points to its corresponding abstraction unary node. Okay, this diagram looks particularly nice, of course, but we can be much more messier. Okay, and why we're interested in unary binary trees is that these properties of some properties of lambda terms can be seen directly on the unary binary tree. So, for example, when a lambda term is closed, then it's to say that a variable abstraction map is complete. And for linear terms, of course, they are all closed because they are bijections. When we say that a term is unitless, it means that it has no closed subterm. And later we will see that we can also see it combinatorially. A lambda term is normal if there is no beta reduction. That simply means on the graph, it simply means, thank you. It simply means that if we avoid this little pattern, that is a binary node with its left child a unary node. So in this case, it's normal. And in particular, what we will be interested in this talk are RL planar terms, or I just simply say that they are planar terms, in which we ordinate the variable abstraction map in the right to left fashion. If it's not so clear, I can another formulation would be, well, in this diagram, we always point the arrows in a clockwise order, and we pick always the first one that is available. And we pick them and we ordinate them so that it can be drawn on a plane without crossings. Okay, for these terms, for these planar terms is in particular particularly interesting. Why? Because in this case, there is one unique choice for the variable abstraction map. We already know it's a bijection, and the planarity actually tells us what the bijection is. It fixes uniquely. So for these linear planar terms, instead of looking at the tree and the correspondence, we can focus simply on the unary binary tree, and that's enough for us. And of course, the study of linear terms, it has been in the focus of folks for a long time, and we have already obtained a lot of results on the proof theory, etc., but also on the enumeration. So in this table that I picked up from an article from Noam, we already have a lot of families of linear lambda terms in which we succeeded in counting explicitly with explicit formulas, and they are all on OEIS. And this is, of course, the accumulation of the work of a lot of people, and some of them are among the audience. Okay, but what's more interesting in this table is that there's two columns. There are three columns: one for lambda terms, the families of lambda terms, another for the sequences. But there is something in the middle, which are another class of combinatorial objects that are called maps. And we have also all sorts of maps. And maybe you don't necessarily, you're not necessarily familiar with these objects. So now I'll tell you what are these objects. So what is a map? It's short for combinatorial map, and simply they are just drawings of graphs on a surface. So we pick a surface, closed surface, so it can be a sphere, a plane, or a torus with two holes, 3 holes, 4 holes, etc., etc. We pick just an arbitrary surface, and then we try to draw a given graph on it. And we try to draw it on the surfaces so that the edges cross only at their ends, so only at the vertices. And then now we have a surface with a drawing, and then we try to cut the surface along the edges. They are broken into pieces, of course, and we want these pieces to more or less be polygons. That means we don't want a hole in it. We don't want a handle on it, let's say. And if a drawing satisfies this condition, we say that they are a combinatorial map. So these are two examples of combinatorial map, one on the plane, the other on the torus. And in the enumeration of maps, we consider only routing maps, in which we mark one of the corner on the outer face, well, on one of the face. And we say that the face containing the marked corner is the outer face. So for the planar case, we choose to draw the outer face as the infinite space, face like this. So because maps are just drawings of graphs, so many notions in graph theory, they can be transported to maps, and we can talk about planar maps. Well, planar is more or less already in the notion of drawing, but we can also talk about cubic maps, bridgeless maps, which has no bridge, loopless map, which has no loop, bipartite maps, etc., etc. And of course, we can also impose connectivity conditions on it. But we see that there are also a graph in the lambda term, which is the diagram that we just draw with the arrows. So in fact, in the previous edition of CLA, Noam and Jason Reed, they are interested in considering these connectivity conditions on planar linear normal terms. You think if we impose the connectivity condition, which are the terms, and do we have some proof theoretic properties on it? So what are the connectivity conditions we are considering? They are considering here is the edge connectivity. So a graph is called K connected if breaking any K-1 edges in the graph would not disconnect the graph itself. So for example, what we call a connected graph is also a one connected graph, because breaking any zero edge, it is still a connected graph. Okay, so this is a bit trivial. A two connected graph is like when we break one edge, it is still connected. And when we look at two connected diagrams, we see that a diagram is also is already more or less connected with its skeleton. So it's always one connected. But if we have a closed subterm in the lambda term, then in the diagram we will have a bridge, because in the subtree on the skeleton, there will be no edge that goes out of this subterm. So disconnecting this edge will disconnect the term. So this corresponds exactly to what we call unitless terms. Then for free connected, well, already this is not very trivial because cutting any two edges, well, we need to consider a lot of cases. And using some computational experience, Noam and Jason Reed, they conjecture that free connected planar linear lambda terms, normal lambda terms, with n plus 2 variables, they are counted by this very nice formula. How they found this formula is that they compute the first terms, they put it on OEIS, and there is the formula on it. We have the number of OEIS on it. And because it's already on OEIS, it means that it's already counting something. And that something is called bipartite planar maps. Okay, so with this kind of conjecture, we are inclined to try to find a bijection for them between these two families. And indeed, in the next edition, Yakasia and Guanru, who had worked a bit on it, first, they found a combinatorial characterization for free connected terms, because we need to know what these terms are before counting them, of course. And then they try to use this condition to obtain some bijective results to do at least relate some subfamilies in each part on the map side and on the lambda term side to relate them together using bijections. So they have some partial results, but on very restricted families. And what I did for this is that I used their characterization and I constructed a direct bijection between the two families in question counted by the same formula. So we have a bijection. But of course, we are not going to stop by just having a bijection. Why? Because we can use the bijection to do a lot of things. First, the bijection is simple enough already. And because it's simple enough, it transfers a lot of interesting statistics between lambda terms and planar maps, planar bipartite maps. And because we have this transfer of statistics, we can write the generating function of lambda terms accounting for these statistics. And then, because it's in bijection, it's the same as the generating function for maps, which we know too well. We know too well. And then, because we have already done a lot of research on planar maps, we even have some probabilistic results that can be transferred to these free connected lambda terms, just using a bijection without any effort. For example, if we take a very, very large free connected lambda terms, and then we count the initial abstraction, so the initial chain of abstraction, how long is it? It's a random variable, of course. And in fact, the probability that we can the distribution converges to something that's very close to a geometric distribution. And in fact, we have the exact expression of the converging probability. And to obtain this, I did nothing. I just searched in the literature for the corresponding results on maps, and then I copy the whole result and changing the words. Okay, so this is our first contribution. The second contribution here is that we realize that the same kind of approach applies also to general planar linear normal terms. So using the same kind of approach, we constructed another bijection, which is also direct between general planar linear normal lambda terms to planar maps, which we already know the correspondence. And when we restrict this bijection to the terms that are unitless, so without bridges in the diagram, our bijection gives what we call loopless planar maps that are the planar maps without loops. well, you see that the bridges are turned into loops. But in fact, in the study of maps, we can take what we call a duality and to transfer loopless into a loop into bridges. So in fact, we have a bijection between loopless maps and bridgeless maps. So they are the same, more or less. And of course, this is less new as a result because there are already a known bijection when they found the result in the first place by Noam and Alan Shulgeti in the audience. However, the bijection is recursive, so it's less easy to see that it is a bijection, less easy to manipulate, less easy to see the statistics. And they work on a similar notion that is LR planar terms, which for combinatorialists is exactly the same because it's exactly the same unary binary tree. But there are some other issues in the proof theory for this term. So, but I don't know a lot about it, so I'm not going to talk about it. Okay, we are good. Now we go with the bijections. But just before that, we need some notion, basic notion for these bijections. We have mentioned at the beginning that I'm going to just look at the skeleton, which are unary binary trees, well, with some conditions that I'm going to detail now. And for these unary binary trees, I will define three statistics. The first one is the number of the unary nodes in the tree that I denote by unary. And in lambda terms, it corresponds to a number of abstractions. Okay, and then the second is leaf. It just counts the number of leaves. So they are variables in the lambda term, of course. And then the third, called excess, is simply the number of leaves minus the number of unary nodes. And in lambda calculus, it's just the variables that are not bounded by abstractions. So they are just free variables. Okay. And then now we're going to describe the conditions we'll need for the for unary binary trees to be linear planar terms with plenty of properties. So I'll use a little bit of a new notation. That is, I will for a node U in the unary binary tree S, I'll denote by SU the subtree induced on this term on this node. And then we say that the unary binary tree is linear if it has excess 0. And if it's normal, if it avoids exactly the pattern we have just mentioned, that the left child of a binary node is never unary. Okay, and it is one connected if for each node, the excess of the induced subtree is larger or equal to 0. But we already see that all the lambda terms are connected. And in fact, this condition simply says that the term should be well scoped. Okay. And two connected means unitless. The condition is that the excess of any subtree should be strictly larger than 0. It's just to say that there is no subterm that is closed. Okay. So these are the conditions. And then for the free connected terms, we'll need the conditions for free connectedness. And that's where we need the characterization. So I will first start with a small observation that for the skeleton of a free connected planar term, the left child of the first binary node here must be a leaf. Why? Because if it's not a leaf, then it's a tree with some variables. Okay. And if we have two trees like this here, because we can suppose that is two connected already. So there must be three variables in these two trees. Then they must be captured by the initial link, the initial abstractions, which are separated in the middle. And to disconnect the diagram, we only need to delete this edge. Okay. What? 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 What happened? What? What happened? Sorry, throw your system.
Oh, I don't know how to use it. We can try to unplug it and replug it.
Okay.
Was there any preliminary to this? Well done.
Okay. Sorry for that. Where was I? Okay. So this is not possible because in this case, we delete two edges and it becomes disconnected. So it's not free connected. So it means that the left child of this first binary node must be a leaf. And we can just ignore the whole part here because we know that there's no extra structure here. And we consider what we call as reduced skeleton, which is simply the right subtree of the first binary node. Okay. And then the full characterization given by Kasia and Guanru is the following. For a unary binary tree to be a reduced skeleton, it has to satisfy the following two conditions, which are also sufficient. The first one is normality, just the principal one we talked about. We avoid a certain pattern. Okay, and the second one stands for free connectedness. I call it like this. Is that if we have a binary node and we look at its right child, then the free variables, the excess of the subtree induced by right child must be strictly larger than the number of consecutive unary nodes above the original vertex. Why? Because if it is not strictly larger, it means that all the free variables by planarity, they will get consumed by this chain of unary nodes. And in this case, we just cut the edge just above the consumed chain, and we cut the edge to the left of the node U. Then we disconnect this part. And this is not good because we want a free connected term. So this condition is necessary for the term to be free connected. What is surprising is that it is also sufficient. And why I call it surprising, because you probably need 2 pages of very detailed case analysis to prove that this is indeed sufficient, but it is miraculously, after analyzing all the cases, sufficient. Okay, so with this condition, we can try to do the real bijection. And first, I'll introduce an intermediate object called degree tree. It is simply a plain tree with some labeling on the nodes. For the leaves, they have label 0, absolutely. And if for internal nodes, if you have some children, the contribution of each children to the label of the parents is 1, the node itself, plus its label. Okay, mostly like this, except that for the first child, its contribution can vary from 1 to its due contribution. So the maximum label for a node is the sum of the label of its children plus the number of children. But we can take away, well, for example, on the edge, we can take away some of them, some part of them. But the most we can take away is the label of the leftmost child. Okay. So I take an example. If we consider this node, if we want to know what its label can be, well, we sum up all the label of its children is 5, and it has 3 children, so the maximum it can take is 8. However, because we can take away some of the contribution of the first child, it can vary from 8 to 3, because we can take away at most 5. And in this case, we take away 2. And in fact, we can just imagine that the 2 is kind of get robbed on this edge, and we mark the 2 here on this edge. And we see that, in fact, the labeling on nodes and labeling on edges, they are more or less equivalent. If you have one, you can compute the other. So we are going to use them interchangeably. Okay. And with this degree tree, the first thing we can do is for the bijection, is to convert a free connected term into a degree tree. What do? We take the skeleton, we add an extra node on above all of them, okay, as the roots, and then we perform 2 things. The first one is that we smooth out all the unary nodes. So in this case, we get a binary tree on which, a binary tree on which some of the edges have some labels, okay? And then we perform the usual bijection between planar trees and binary trees. We get a binary tree, and then for each node, we say that its right child would be the rightmost child of it in the plane tree, and then if its left child would be its left sibling. Okay. So for example, this can for this chain of node, it's converted into here. So we have a tree with some labels on its edges, and we just flip it left to right, and we get a tree with labels on its edges. And this, in fact, corresponds to the edge label version of degree trees. And then we can translate the labels on nodes and get a degree tree. And we can see that this somehow goes well with lambda terms, the philosophy of lambda terms. So we may say that the rules for degree trees, they are a bit strange, but in fact, if we observe that the label of each node, they correspond to exactly the number of free variables minus 1 in the subterm, then the rules get explained really quickly. For example, if we want to consider the possible label for this node, possible labels of this node, we'll see that it's just the possible number of free variables in the subterm. And where are the free variables? Well, they can be in this tree, or this tree. So when we sum them up, they would be, well, inductively, the label of the children here plus 1 for each node themselves. And because it's the number of free variable minus 1, we are omitting this free variable here. Okay. So we get a sum them up thing. This is the maximum possible. However, we may take out some of the variables using abstractions. And what's the maximum we can take? According to the free connected condition, the maximum we can take is at most the number of free variables minus 1 on this subtree. And this is indeed the first subtree in the plane tree. The label of the first child in the plane tree. So in fact, the free connected condition corresponds exactly the rules we impose on these degree trees. Okay, are you convinced? More or less. The second part, given a degree tree, we can get a bipartite map, but that will take another talk because it's very long. I just roughly explain that more or less it's an exploration procedure on planar maps. When we have edge, when we have bridges, we kind of do nothing. We kind of do more things. And when we have faces, we open them so that we can get, well, we can get a tree. And then whenever we open them, we have an edge with some labels. And that's how we can convert a bipartite planar map into a degree tree. And in fact, it's also related to what we call a Chambordon's new interval in the temporary lattice. But that's a parenthesis. And in fact, using, well, without looking at the details of this bijection, just using what we have talked about, we can see some of the statistic correspondences. For example, the unary trains in the lambda term of length k, they get converted into a label that is k. Okay, and then in this bijection, we see that we put labels if and only if we see a face of degree 2k. So in fact, the unary trains of a certain length corresponds exactly to the number of faces of degree 2k of a fixed degree. And this also applies to the initial unary chain and the degree of the roof face, the outer face. And that's how we get the probabilistic result. Okay, are you convinced? More or less. And because I don't have a lot of time for the second bijection, maybe I'll just skip through it, but the idea is more or less the same. I'll just say that we recall the conditions that the one connected is well scoped. The excess must be positive. And we use another family of trees that is called V trees, which is a plain tree with a labeling on nodes, of course. But we changed a bit the rules. For the leaves, they can have labels 0 or 1. And for other nodes, they can have the maximum label, the sum of all the labels of its children, plus 1. But it can go down to 0. Okay. And you can see that this is really close to lambda calculus because we are going to do exactly the same bijection. Well, more or less. At least for the tree part, it's exactly the same. But for the labels, what we are going to get is that for each node, we'll label it by the excess of its right child. Okay. And in this case, we see that if we get the sum of all the if we want to count the number of free variables in this whole term, it would be the maximum possible. It would be the free variables here, here, and here, which is simply the labels of its children, and plus 1 for this one. This is the maximum possible, but we can take away some of them in the abstraction, using the abstraction. And in fact, we can take as much as we want, as long as it is well-founded, well scoped. So we can take away all of them just up to 0. Okay, up to having 0 free variables. And in the case when we have 0 free variables, what we get is a closed subterm. So each time when we see a 0 label, it means that we have a closed subterm somewhere. And it also explains why on the leaves we may have 0 or 1, because we may have, of course, the leaf can be a variable. In this case, it's a 1 because it's a free variable. But it's also possible that it is a free variable, but it gets consumed directly by an abstraction just before it. So 0 corresponds to closed subterms. And for the bijection itself, I'm not going to explain, but it's more or less like an exploration procedure that's similar to the previous one. We kind of open the edges, etc., and the labels are given by the number of vertices on the outer face. And this is very interesting because the only time we have the label 0 is that we have exactly 1 vertex on the outer face, and that corresponds to a loop. So it means that if we restrict to unit list terms, we'll get trees without zero labels. That means we'll get trees without loops. So they are loopless trees. So we see that this restriction to unit list terms is very natural. Okay, I hope that you are more or less convinced. And here is a recapitulation of the results I talked about here. We have two bijections. The first one is new because it connects three connected terms to bipartite planar maps. The second is now it's a new bijection for an old result, but it's a bit easier to manipulate. They are not exactly the same bijection in the sense that if we restrict the one for general terms to three connected terms, we don't get the first bijection. However, you have already seen that the spirit is more or less the same. Okay. And now, of course, we can try to explore other enumeration consequences of these bijections, and we can also try to look at a higher connectivity. But I'm not very. It would be a hard work because free connectedness. Two connected lists, it takes 2 lines. 3 connected lists takes 2 pages. If we look at 4 connectedness, it would be, well, 10 pages, I don't know, but maybe we can look at it. So thank you very much for your attention. Yeah, thank you for listening.
Yeah, so thank you very much. So are there questions here or online? Again, if you have questions online, then please raise your hand so we notice it. Martin?
Yeah, thanks. You mentioned some statistics regarding the number of leading abstractions.
Yes.
So have you studied how they compare between different classes of lambda terms? You mentioned that it was almost geometric here.
Yes.
And is it any different in normal linear lambda terms? Without
Okay.
the
In normal linear terms, they correspond to the number of vertices on the outer face of a map. I didn't exactly find that result in the literature, but from experience, they should more or less have some kind of similar, close to geometric distribution, and they can be computed explicitly. And it's the same for 2 connected terms. I didn't do the computation, so but they don't have a drastic change in behavior.
And if I may, a second question would be: so you also said that you had some generating functions.
Yes.
Correctly.
Yes.
So is it simple enough that you can do Boltzmann sampling or something like this?
Can you do Boltzmann sampling on bipartite maps?
I don't know. I don't know too much about maps.
Yes. Yes. Is it? Yeah, probably.
Yeah.
If you restrict yourself to a fixed profile of phase degrees, it's possible. It's possible. It should be doable. Even not Boltzmann, but exact sampling should be possible. But Boltzmann on bipart, you can do exact sampling on bipartite maps. Right. Yes.
The parameter, the number of abstractions, leading abstractions.
Yes.
It's captured by catalytic variable, or it's just something.
It's a catalytic variable.
Yeah, so it's nice because if you do Boltzmann something based on maybe you can tune this parameter to if you want more or less abstractions. Yeah, I find nice.
Yes, it's doable. It should be doable. Yes. 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 I'm kind of sure.
It looks like we have a question from Alex. Alex Singh. Alex, are you there?
Yes. So can you hear me?
Just saying that behind the.
I don't know if you can hear me. Let me see.
Yes. Okay. And do you have a question?
Yeah.
No, I saw you raised his hand, but
Yeah, I do have a question. I don't know. Can you hear me? It's no.
Yeah,
Okay.
I have a question, but maybe so since I missed the beginning of the talk, maybe it's a stupid question, but
It's good because I have a microphone here, but let me just check. Let's mute the other people.
okay, very good. So my question is, for planar map, you can go to 4 connected and then 5 connected, and then it stops because of planarity.
Okay. Yes.
So does it make sense to have arbitrary k connected linear terms or planar linear terms?
Maybe not, but it depends on which kind of notion of.
Yeah, well, that's my question. I missed the beginning of the talk, and I shouldn't ask question about things I didn't hear about. But is the notion of connectivity equivalent to that of?
No, it's not exactly equivalent because there can be, if I recall correctly, there can be some exceptions, some minor exceptions.
And because it's already, this is talking the terms seen as maps are 3-valent, and so already they're not 4 edge connected in the usual sense, but Tat called them internally 4 edge connected, meaning that the nodes themselves are exceptions. So the only kind of 3 cut is a node.
It's for nodes. So for the very small inevitable cuts, I think it is in this sense.
Alain?
Can you show again the slide 15? It's about the definition of trees.
Okay.
I'm not sure, but maybe not this one. Yes, this one. It makes me think of the notion of well-labeled trees by Corey and Vauquelin. Do you know?
Yes.
Is it the same or?
No, it's not the same.
Okay, thank you.
But it's we can see that they are more or less the family of beta trees, beta labeling of trees, or alpha beta labeling of trees, which is in the what we call the description trees of planar maps. That follows some kind of rules about the labels of the parents can be computed from the labels of their children with some ranges within some ranges.
So thank you, Wenjie, again for the very nice talk. And where's the recording?